of the webinar. In the meantime, I'm going to introduce the topics of causal inference, detecting causality through statistics. One very important topic in today's whole scientific world, I would say, but especially important in fields like biostatistics, data science, and so on.
Sorry for that.
A little bit about speakers. So I'm Darko Medin. I will be speaking about different aspects of causal inference. Justin Belair, fantastic data scientist and statistician, will also discuss his experience and various topics related to causal inference as well. So we will be discussing three main topics, which is study design versus causal inference. What do we do when we cannot achieve a study design for causal inference? So we'll be discussing topics such as propensity score matching, inverse probability, weighting, instrumental variables. And very important, we'll be sharing practical experiences from real-world projects, and of course, discuss some resources that anyone can use in the field of causal inference. Now I will introduce myself. I'm Darko Medin, an international expert working with different companies around the world in fields of clinical biostatistics, clinical research, but also in the fields of digital products related to data science, machine learning, AI. I will be discussing some of my experiences in this webinar, which are from various fields. Some of those fields are from clinical research, such as clinical trials and real-world evidence, but I will also be discussing some angles on using machine learning for causal inference as well. Enough about me. I will now leave it to Justin to introduce himself, and would really love to hear many details about him as a fantastic professional in this field. And of course, we'll discuss a lot of details later as well.
Thanks, Darko. Quite the introduction. So everybody, I'm Justin, and I'm a biostatistician or statistician, data scientist, all that good stuff. And I've been working now for quite a few years as a consultant. So I work with academics, mostly in subjects related to biology. So a lot of medical clinical trials, obviously, but also I work with people in agriculture, people in different biological fields. And around the same time I started doing this, so I was always passionate about science and how does science work and how do we learn things by looking at the world in intelligent ways. And then that's kind of when I stumbled on causal inference. So I started reading about that, and I realized that it's kind of like part of what statisticians do, maybe without knowing, but also it goes a lot deeper, and a lot of social scientists use it. It's used a lot in epidemiology, and that kind of was really an interesting moment in my development, where I started reading so much about causal inference and started to use the principles that I learned to think about how to do statistics effectively, to think about how to discover cause and effects relationships, but also as a set of tools, right? Like Darko mentioned, propensity score weights or matching or instrumental variables and things like that, that I kind of already heard about, but I didn't realize they were part of this large framework that we call causal inference. And so I kind of realized that there was a lot of interest on LinkedIn. So I created a causal inference group recently, which some of you might have already joined. So that's really exciting. There's a lot of people that are interested. So I think we can build a nice community around this really fascinating topic that is causal inference. And also, I haven't announced it yet, so I'll say it here exclusively. I'll announce it soon on my profile, but I've also started writing a causal inference book for statistics, biostatistics, and related fields. So I'm really like in the the weeds, if we can say, of writing. So I have a lot of things on my mind, and I'm really excited to share them with you today. So let's jump into topics. I just want to remind you that we're really open to getting questions. So write questions in the comments. We'll answer them at the end. And if we don't have time to answer them on video, we'll reply in the comments. It's really, personally, it's my favorite part. So please don't feel shy to share any questions. So Darko, can you please maybe introduce our first topics of the day, and we can go from there?
Fantastic introduction, and I must say, Justin, can't wait for your book to be finalized. Really a fantastic announcement on today's podcast. Thanks. Okay, let's jump to the topic. So one very interesting aspect about a lot of statistical results is that a lot of those results are inferenced by association. So a lot of people try to find associations between variables, try to analyze results by just finding association, and p-values could be there, correlation coefficients could be there, regression coefficients could be there. So a lot of different results could actually mislead if causal inference perspective is not taken into account. So one example is that if one was to make a correlation matrix on observational data, most correlations, let's say 50 correlations were found there, most of those correlations would not be meaningful, and they would not be causally associated variables. So that's why it's important to include other angles and other perspectives to try to find causal associations which are more rigorous, which are more credible, more validated. And for that reason, it's not easy to get to causal, the notion of causality. But it's very important because a lot of scientific fields depend on causality. So clinical research, clinical trials, real-world evidence. You mentioned fields in agriculture, other life science areas. A lot is dependent on answering the causal questions. And there are three main fields, three main topics, which are very important. One of them is study design. So causality is very difficult to achieve without specific study designs. We have some examples that we'll be discussing later. For now, I'll just mention that as a topic. There are special statistical approaches that one can use, such as propensity score matching, inverse probability weighting, instrumental variables. There are even machine learning and AI approaches which are combined with these, which could be used in different fields. For now, I just want to say that causality is not easy. It's not easy to establish, and yet it's very important. So special approaches are needed to establish it. One of the most important aspects is having the right study design. And we will be discussing today various definitions such as counterfactual study design, randomizations, and so on. Would be great to hear from Justin about this topic, as I know he's very experienced in different study designs related to causal inference.
Yeah, so as you mentioned, right, a lot of questions we ask are about cause and effects, right? So if I eat 2 liters of ice cream, I don't feel good, okay? So that's a cause and effect relationship. We're also interested in sometimes counterfactuals, right? So if something changes, let's say I imagine that yesterday I didn't eat 2 liters of ice cream, maybe I would have felt better today, okay? So that's kind of a counterfactual. And we also are often interested in the effects of what we call an intervention. So if we intervene, let's say we give a vaccine to the population, what's going to happen to the spread of a disease, for example? So to answer these kinds of questions, especially related to interventions, right? We know that we can do randomized controlled trials. And we won't go into the details of why, but essentially the idea, the most simple kind of control trial we could do is a fully factorial experiment. So we have treatments, let's say we have two we want to compare, and we just give them to two different groups, and we compare the groups, okay? So this experiment is like maybe the simplest idea we can have. We give all the treatments we're interested in to different groups, and we look at the groups. So this comes from ideas related to agriculture. So I worked on a trial like this, where we take a field of land, we divide it into, 10 plots, and in each plot we give treatments, and we look at the end of the season how much corn came in each plot, and we look, okay, more corn was there than over here, so probably this treatment is better. And that's kind of like the basic idea of how we design an experiment. And then we can go into more complex designs because we have certain things we're more interested in, or we have limited resources, or we have different constraints that force us to be more creative in the experiment. But these are really like a tool that we use for causal inference, and it was long thought that it was the only tool we could use for causal inference. But today we know that it's not true. But maybe I think Darko has a bit more experience with this principle in phase 3 clinical trials. So I thought maybe you can say a few words about that, Darko.
Thank you so much for a fantastic discussion, Justin. That was really a great experience you shared there, and I will try to connect with some of the topics that you were discussing. So, as Justin was saying, a lot of details in causal inference depend on control of the experiment. There are other approaches which don't have to be associated with that, but a lot is about controlling certain aspects of the data. One such aspect is confounding. So just to relate to what I was saying previously about correlations, most correlations in observational data come from confounding, or some third variables which are not adjusted for or not accounted for initially. They could cause many variables to be correlated but not causally related. And there is the problem of confounding, one of the most important problems in causal inference. Obviously, clinical trials are designed to be very rigorous and to have specific methodologies implemented to deal with confounders and to isolate the experiment, isolate the variables in the experiment. In phase 3 controlled trials, this is very rigorous, and that's why many would say that phase 3 controlled trials are the gold standard of life science research. But the reasons behind this are really in the causal inference. Phase 3 controlled trials are 99% designed for causal inference. One of those aspects was exactly what Justin was mentioning, which is the counterfactual design. So we usually have control groups. It could be standard of care groups, placebo receiving groups. So those groups are used to control for that counterfactual aspect. And then we have intervention, exactly as Justin said. We have control, we have intervention, and that's what makes one of the principles needed for causal inference. Another principle which is very important is the randomization. Randomization is probably one of the most important segments of phase 3 clinical trials. Many think that randomization is there just for removing the selection bias. This is totally wrong. This is a very superficial interpretation. Randomization is there to correct for many types of bias. It's there to correct for bias originating from known variables, but very importantly, randomization is there to correct also for unknown confounders, for potential latent variables. And this is why randomization can isolate the variables that we are interested in. In phase 3 clinical trials, it's usually we have a control group and we have the intervention, we have the treatment. So we want to see what is the outcome of this treatment. Does a specific treatment or drug X work better than standard of care in certain population? So to do that, we need causal inference. We need to isolate the effects of the confounders as much as possible. So counterfactual design, randomization combined, they are the core of causal inference in randomized phase 3 controlled trials. There are other details which are very important, such as time to event data, right? Time is another very important aspect in causal inference. We know that causality is time related, and that evaluating time aspect in a study is also very important. We'll discuss about this in more details later. For now, I will just introduce these topics and maybe say a few words of when would one need a different approach. So this was an approach where one can actually perform, a research company or institution can actually perform a randomized controlled trial. What happens when randomized controlled trial is not feasible? Frequently, randomized controlled trials are very expensive. They take a lot of time, and sometimes they're not even feasible for ethical reasons. So there is a huge amount of data that is generated in non-experimental scenarios, in scenarios of generating real-world evidence from hospitals where treatments are occurring in a non-simulated, non-experimental environment. Actually, majority of biomedical data is from this field. So statisticians have developed various approaches to deal with that situation when we cannot randomize the data, we cannot get fully controlled experiment. So we use different approaches, such as propensity score matching, calculating inverse probability weights, using special variables, which are very important, instrumental variables, but all this requires both statistical and domain knowledge. That's why I said causal inference is not easy. A lot of experts in this field need to have a multidisciplinary knowledge, especially domain knowledge of the topic that is being studied. So I will stop there. I just introduced these topics. I think Justin has expertise in fields such as confounding. We discussed this many times, and I'll stop there and let Justin explain a very important topic, which is confounding.
Thanks, Darko. Yeah, so just to maybe continue on what you were saying, right, which was great. So thanks for sharing that. The idea, right, of controlling the experiment and randomizing the treatments is really a key idea in causal inference. Why? Because let's say we give the treatment and one of the groups, we didn't randomize it, and the doctor gives the treatment to the people he thinks that will benefit from the treatment, right? So he doesn't randomly choose. He actually decides that based on his judgment, he's going to give the treatment to those that should benefit from it most. Well, then if we take that group, it's going to be biased. The treatment effect is going to be biased because we're going to have selected people that we think would benefit from the treatment to be treated. So the idea is that if we don't do a controlled randomized experiment and we just look at how things are happening in the world, right? So we call this real world evidence or observational data. It has different names, but we kind of have to, we can't just look at, okay, who received the treatment, who didn't receive the treatment, and compare them. Because this comparison will be biased for a bunch of different reasons, like the one I just gave, where Well, doctors give treatments to people that should benefit from them. They don't just randomly give out treatments. Or we can think of other settings where we look at, I don't know, people that choose one university versus another. Well, maybe the people that choose the university want to go there because they think it'll be better for them. And the ones that went to the other one, they just didn't get accepted in the other university. And now we're making a biased comparison. We can't say that this is the university that necessarily makes things better and things like that. So when we're looking at the real world, there's a bunch of these sort of confounding patterns in the data. We can't just compare groups as if they were similar. We have to make sure that we can make meaningful comparisons. So we have a bunch of techniques to do this. One of the main tools that statisticians use is propensity score modeling. And this is important for different reasons. It's really important in the theory behind why this works, but it's also important because it's a convenient tool to eliminate confounding from observed variables. So take the example that Darko said, where we record a huge biomedical database from a hospital or something. Some scientists or some researchers are thinking, hey, this is really interesting data. Maybe I should pull all that data and try to answer some questions that are interesting. If the researcher doesn't think about the different possible confoundings, right? So I don't know, people in this group are a lot older, or people in this group are not representative of what we would expect in another situation, or things like that. The associations we're going to measure are going to be biased. So when we have a lot of variables like this, and this is a kind of study I've worked on before, we can use all the variables that we think are confounders, or that we have good reason to believe that are confounders, and use what we call a propensity score model to try to eliminate that confounding. So in the example I'm talking about, we had, it was observational data just from a database. We did a lot of cleaning. We had like a population of about, or a sample, we could say, of about 1,000 patients. And there was two things we were trying to compare, but we know that this comparison is biased by, I don't know, 30 other variables that we measured. So we take these 30 variables, we put them in a magic tool called the propensity score model. And then we can use these propensity scores, which are a sort of model of how people are given the treatment or the control. We can use this tool to eliminate confounding. Now, we're always limited by the problem that we don't measure everything. We don't observe all the variables in the world. So then we can even go further and do other types of analyses to make sure, okay, there's still some confounding that comes from variables I didn't measure, but maybe I can prove that it's so small that my conclusion is still valid, right? And we call this sensitivity analysis. We can do a bunch of things like this. And the main goal always is to try to think in terms of, okay, I have a causal effect that I want to measure. How am I going to measure it? So there's different ways to think about it, but one of them is to think, okay, let's imagine that we could have done a randomized control trial. What would that trial look like, and how would I analyze it? And this is a technique that statisticians use, but there's also other tools, for example, instrumental variables, which were used a lot in social science and economics. I actually learned about them in economics class. And I know that Darko had a few experiences with them and a few things to say. So maybe I can just let you continue on, Darko.
Yes, thank you so much, Justin. That's exactly one of the most important topics that we were referring to in the scenario of real-world evidence, where we cannot actually perform a fully controlled experiment. Propensity scores are one of the main tools, one of the go-tos for statisticians to actually resolve many problems. Justin was in detail describing one of those problems, which is confounding by indication. We just cannot simulate everything in the real world evidence, but given that we have enough important variables and enough samples and use the right approaches, we can get as close as possible to that scenario where a significant portion of confounding is removed, and we can start looking at the causal average causal treatment effects. Justin explained exactly what is probably the number one go-to in causal inference of observational data. The second approach, which he mentioned, was the instrumental variables, which is also important because instrumental variables are specific and they can be used in a situation where propensity scores cannot. So propensity scores are usually calculated from the covariates, so from the covariables, the context data that we have in real-world evidence. Usually there is a lot of context data. That's why this propensity score approach is very good and can be used in many situations. But there are situations where the data that we actually have in real-world evidence scenario cannot be used to accurately calculate propensity score. So we need to shield the analysis from the potential unknown confounders, and that's where instrumental variables come in. So instrumental variables are an alternate scenario in situations where we cannot use propensity scores. So they can shield the analysis from unknown confounders, and the main principle behind that is that instrumental variables are variables that can be identified using domain knowledge. So these are the variables that are associated with the cause variable, which are associated with the effect variable, but not with the cause variable. So one very important aspect is that the variable that we define as instrument is based mostly on domain knowledge. So we cannot just calculate a correlation or regression coefficient to say, okay, we could use this as an instrumental variable. We need to know for a fact, based on domain knowledge, that variable can serve as a good instrument. And that's why I said previously that instrumental variables are one of those areas where domain knowledge is very important. So combination of domain variable, domain knowledge about variables, and statistical knowledge about variables is very important. So basically, we can use it to remove the confounding in addition to propensity score matching, or when it's not applicable. Now, there are other approaches which can be combined in a real-world evidence scenario, because real-world evidence is usually very abundant in terms of having large amounts of data present. So this makes it ideal for utilization of methods such as machine learning or even AI. So implementing methods such as random forests or even deep learning can be used to augment some of those causal inference approaches that we use. So causal inference, machine learning causal inference, is basically a very simple combination of the approaches that me and Justin were mentioning, so propensity scores, instrumental variables, counterfactuals, combining those with the scalability and efficiency of machine learning models to create something that's called causal machine learning. Now, causal machine learning is still a developing field. So there are huge developments there. Dynamics is high, but it's still a developing field. Many researchers, many institutes and companies are still in the phase of adoption of causal machine learning. But I think huge potential is there, exactly for the reason of we have a lot of data that's created on a daily basis in hospitals, research institutions, and data repositories also store huge amounts of real-world evidence. So methods that can scale the analysis to perform analysis much more efficiently while maintaining these principles that we were mentioning about causal inference, that's one of the most promising areas, I think, in the future. And a lot of developments are happening right now in that field. So I think causal machine learning, or causal ML, as we would alternatively call it, probably causal AI. So causal AI is probably the next topic, because a lot of companies are now developing AI models to mimic human intelligence. And one of the topics, one of the goals that need to be achieved is machines would need to reason similarly to humans. So humans are inherently made for causal reasoning. A lot of things that are happening around us in the world, a lot of phenomena, we are naturally reasoning them causally. What is happening when something else happens? Why is something happening? What is the cause for this disease? How could this disease be treated by targeting a specific cause? So we're naturally doing that, and when machines also start doing that, that will be a step closer to what everyone is calling artificial general intelligence. So a lot of companies are investing in that field too, and I think anyone interested in causal inference, it's a very dynamic field. It's a very interesting field, and it's needed. It's needed for further development of science. So I'll stop there, and we've opened a number of topics, and I will now leave to Justin to discuss some very important aspects we were discussing before the meeting, and really looking forward to joining the discussion about it.
Thanks, Darko. So I think it's really interesting, maybe just to add a few things and then jumping into a new topic, the idea of using machine learning, right, which are somewhat related to statistics in a sense, right? We're building models, but we have a different kind of approach than traditional statistics. And there's a lot of emerging tools. So maybe I'll just go over a list of what I think are like the most important things to know for statisticians or for biostatisticians if they want to start thinking causally. So you'll realize that if you start learning causal inference and you're a statistician, that maybe a lot of the things that you kind of already knew are now made explicit or made formal. And this is a really great tool just for your knowledge to understand, like, why am I doing this way? And why is this causal? Why is this not? And then I'll end maybe with an opening about the new frontiers, right? Like machine learning, and what are the kind of tools that are being developed that you can start learning maybe by reading papers or looking at courses or things like that. So the traditional way to look at causal inference in statistics, so a good place to start is with what we call the potential outcomes framework, or the Rubin causal model. So this is a tool that's important. And then it's a bit abstract. Some people find it difficult. There's also another framework that has a lot of similarities that uses graphical methods, right, that we call DAGs, or directed acyclic graphs. And these methods are, I think one way to summarize why these methods are so popular is a picture is worth 1,000 words, right? So they work by using images, arrows that denote relationships, causal relationships between variables. So these have a sort of intuitive feel. So that's a reason they're used a lot in social science, in economics, in epidemiology, these graphical models. And they also have the interesting feature that a lot of procedures that we need can be developed algorithmically. So we can just build the model, the graphical model of our phenomenon, and give it to a computer, and the computer tells us how to do the causal inference problem. So these are very valuable tools. So I think these are kind of like the foundations, and in the book I'm writing, that's kind of the approach I'm taking. So I think these are foundational tools. They can help you understand everything else. Then once you know these tools, the next steps would probably be propensity scores and instrumental variables, which are important tools to use for problem of confounding and how to look at observational data with an experimental point of view. How can we look at the data as if it was an experiment? So propensity score is a way to eliminate confounding, and instrumental variables is a way to find a variable that's an instrument that we can look at how it varies to kind of estimate the effect of the real variable we're interested in, the real treatment variable. So these are very important tools. And then in a lot of social sciences or a lot of other different fields, epidemiology, things like that, we're very interested in problems of mediation and interaction. So we sometimes call these mediation models. So mediation models are important when, let's say, we encourage students to study more by giving them a tutor, and we want to see how it affects their test scores. Well, we can assume probably that there's a mediator, right? So a mediator means in the middle, a variable that is how much time they study, right? So giving them a tutor might give them motivation to study more, and then that affects their test score. So we kind of have to disentangle, maybe the tutors are just encouraging them to study more, or maybe the tutors are actually helping them, maybe a little bit of both. So this is very important in statistics, and I think it's a very interesting topic. And then I also believe it's important to learn about time varying and time modified confounding. So this, when we have longitudinal data, things can get very complicated very fast because some of the confounders are also varying through time, right? So people, maybe their age is changing, their weight is changing, their blood pressure is changing. So how do we control this when we're studying people over a period of time? Or when we look at, let's say, health records that have been collected over time, and the person appears many times, how do we deal with that? So there's a whole literature on that I think is very important for statisticians. So these are just like a handful of topics. I actually did a post maybe a month or two ago on LinkedIn where I asked, is there any other topics that people think should be learned for statisticians who want to become proficient in causal inference? So I'll send you the link. So maybe you can go look at what the community thinks. Obviously, I would like to know everything, but I didn't have time to read everything yet. And I think maybe before jumping to your questions, I see there's already a few questions that I'm really excited to answer. Darko and I thought it would be good to give maybe some resources that for those that want to start learning or to continue learning about causal inference. So I thought maybe we could start with a few books. I don't know if Darko, you had a few books you wanted to share. I have a few. I don't know if you want to start, and then maybe I go. How should we do this?
Please go ahead. Please go ahead,
Yeah.
Justin.
Okay. So for me, the two, I shared this before, but like I said, I think the foundations are potential outcomes and graphical models. So there's two books. So for the potential outcomes, I think the most complete book is the Imbens and Rubin book, Causal Inference. I have it here. What's it called? It's called Causal Inference for Statistics, Social and Biomedical Sciences, and Introduction. Okay, so I think this is the most elegant and complete book on the topic. And for graphical models, I think the most elegant and complete book is Judea Pearl's book, who kind of invented the whole framework. which is just called Causality. These books are not easy. I kind of enjoyed reading them. So there's also more maybe accessible books. If you kind of start, if you don't have a background in math, you might find it a bit hard because they're heavy on mathematical notation. So some introductory books that are often cited as easy to start off with. So there's the Causal Inference mixtape by Scott Cunningham, who talks a lot about it on LinkedIn. So I think his conversational tone is interesting, and there's code. So there's Stata and R code. So I think that's a good place to start. And then there's The Effect by Nick Huntington Klein, who's also an economist. So there's a bit of overlap there. So I think those books are good places to start. And there's also one called Causal Inference in Statistics, a Primer by Judea Pearl and Gleimer and Jewell. So I think these books are better at introducing the topic. I don't think any book is like really easy. I think that the topic is quite advanced, and it might take time, especially if you're learning it in parallel with statistics or machine learning or something like that. But if you have a background in statistics, I think you're ready to jump to the causal inference literature. So there's a bunch of other books. Feel free to reach out. Like I kind of collect them, so I can help you if you need to get advice on this. But I thought maybe also what would be interesting is to talk about our experience with programming languages and packages. So I know that maybe Darko had a few to recommend here, and maybe I have also. So maybe I can let you speak, Darko.
Oh, thank you so much, Justin. Definitely, I think those are some fantastic resources. I may mention a few packages later. I see we have a few comments, and I see we have very important questions. One of them from Alexander Malak. Thank you so much, Alexander, for joining us, and some fantastic questions. I see one of your questions, and it's straight on point, which is the explanation, to clarify the explanation on instrumental variables. So it's entirely possible that I mix the words treatment and effect, so it happens. Just to clarify for everyone, instrumental variables are those variables that we know for a fact are associated with treatment, but not with the effect. And when I say we know for a fact, means from logic and domain knowledge. So it is entirely possible. I don't want to confuse anyone in the audience. It is entirely possible that I mix those two words, treatment and effect. So another clarification, instrumental variables associated with treatment variable, not associated with the effect variable. And we have another interesting angle that Justin was saying, that a lot of resources are now out there, which was not the case a few years ago. Alexander Malak was one of the authors of a fantastic book, and I strongly recommend to anyone interested in this field. And another great thing is that a lot of R and Python packages were developed over the years for causal inference. So as example, causal machine learning, we have top-level packages in Python, such as EconML, which was developed by Microsoft, I believe, and Causal ML, which was developed by Uber. So some top-level companies are developing. Maybe I'm wrong, so anyone from the audience correct me if I'm wrong about the companies, but I think that's the situation. And there are a lot of packages in R as well, such as IVReg for instrumental variable regression. This one was there for ages. It's one of my go-tos in R causal inference, the IPV, and so on. So there are many packages that are now available as open source packages, and you can check them out. Justin mentioned most of the top level important and I fully agree there. Sources for you, and Justin, is there any specific? I'm looking at the questions. Is there any specific question you would like to address?
Yeah, I just want to add maybe one final resource, and then we can jump into the questions. So for those of you that use R, I suggest you Google Causal Inference CRAN, C-R-A-N. I can write it in the comments after. So CRAN is the repository for R packages, right? And there's this page that looks like a old package documentation page, but it goes over like hundreds of packages that are related to causal inference, and they're all classified according to the topic. So I think this is a great place to start, and you can go see, okay, is the package maintained, or has it the last commit been in 2012? So you can go take a look at that, and you can see the most active packages, and that's a really good way to learn hands-on, right? To actually use the packages and do some work with real data. And often these packages have toy data sets that you can use and things like that. So I just wanted to specify that. I'll put it in the comments if I remember, because I have a lot of things that I said I'd put into the comments. But let's go with the questions. So you answered Alex's question. That was great. Thanks, Alex. We had a question about how do you define a confounding variable? Is it simply a variable that causes both the exposure and the outcome? Yeah, so that's one way to define it, right? We use a graphical model, and we see, okay, it causes both the exposure and the outcome, which in general could create confounding. So, for example, we see that on days that people wear shorts, they're more likely to eat ice cream, and we say, oh, maybe wearing shorts makes you want ice cream, which is kind of ridiculous because there's a confounder, right? It's the temperature makes people wear shorts, and the temperature makes people want ice cream, and that's why we see an association that isn't causal. So that's one way to look at confounding. I think it's the simplest definition. And Alex answered that question in the comments. Thanks, Alex. Do you want to take a question, Darko? Maybe we can go one by one.
Sure, yeah. So let me just check the questions one moment. So I'm looking at the question from James Mayer, I believe, which is about a specific study with Lasix treatment and the frequency of treatments given to a specific animal, I believe horse, if I read well. Mm-hmm. So it's a great question. It's a great question, and I would say that in this situation, it's more important to think about the domain knowledge first, and then define the actual design. So we have the frequency of treatments, which could be potentially used as some form of counterfactual. But in this situation, since we have the time, I would suggest maybe using those, because those response curves are maybe more important than actual frequencies, because frequencies could depend on many things, and it's very difficult to define how would that work for frequencies and the actual domain knowledge. So I see that you have as your target variable, I think, career length for them. So I think it's very important to understand: is it possible from the domain knowledge that this career length could be associated with the frequency of those treatments? So look into that domain, try to understand mechanistically, is this possible, and then move into actually designing a specific study. Do you want to take over, Justin?
Yeah, thanks. I'm just looking. We have a question. Maybe I'm not quite sure. So I'll read it and maybe I can figure it out on the fly. So it's by Juan Carlos. could we deal with information bias when using observational or real-world data, mainly with retrospective or historical data? I wonder about the validity of this kind of data for causal inference. So I think the problem here is that I'm not sure what is meant by information bias. I think maybe it means that what is recorded is not true, or maybe it's the meaning changed over time or something. If that's the case, I mean, I think any kind of data that has problems with the quality of information will be problematic. I don't think it's specific to causal inference. I think it's a problem for any empirical work, really. So if I didn't understand the question correctly, feel free to maybe add more in the comments, but that's what I would say. Darko, there's a question specifically for you, I think, by Alex. If maybe you could find it. You're on mute, Darko, you're on mute.
Yeah, thank you. So there's the second question by Alex, and thank you, Alex, for being so active. It's really an honor to have you on the podcast and ask some very, very important questions and give comments. So I think it was about propensity scores, right? And propensity, what would be favorable? Propensity scores or matching, something like that, if I read well. So yeah, basically they would both be based on propensity, but what I would prefer is the scenario in which my variables are structured better. So if I have a very large sample, I would prefer propensity score matching, because I don't need to collapse the weight of the propensity to one variable. So I can just do matching based on a lot of variables and keep all those variables in the model. But if I had small to medium sample, I would rather go for propensity score as a singular variable to fix or to lower to some extent the confounding by indication. So that's the first thing that's in my head. But I would love to hear this from you. So if you're there, Alexander, it would be great to have your comment there and see what you think. And I think Justin is also checking questions. So if there is the next question for you, Justin, please go ahead.
Yeah, I think I'd just add that with propensity scores, there's a whole bunch of ways we can use them, right? There's matching, there's weighting, there's using them as a covariate and things like that. I think there's a lot of papers that do simulation studies to see when and with, like when one method is better than the other. I think there's not a universal answer, but I think what you said, Darko, is interesting, right? When you have the luxury of having a lot of data, you can maybe do some matching that's precise without having to collapse everything to the propensity score. So the next question is from Sean. It's a very interesting question. If I can just get my phone to not... Sorry, I'm trying to read it. So Sean says, thank you for the informative seminar. I have always seen propensity score matching within a frequentist framework. Are you familiar with ways this can be achieved using Bayesian methods? In principle, it seems possible. You just match people and then estimate, but obviously using priors may complicate this in some way, perhaps because we may need to treat people as some kind of random variable. For example, the matchit package in R allows easy matching, but I'm not aware of an R package that supports a Bayesian method for the same thing. Yeah, that's a pretty deep question. I'm not off the top familiar with how to do this. I know that, for example, in the Imbin's Rubin book I told you about, and in a lot of papers that Rubin wrote himself, he's in favor of Bayesian methods for causal inference, right? Which in principle are appealing, right? They're interesting for different reasons. So part of that is to use a propensity score model. Basically, the Bayesian approach that Ruben advocates for is similar to using imputation models, where we impute the missing potential outcomes using a full Bayesian approach, where we have a model for the distribution of the potential outcomes. And then we use Bayes' theorem and De Finetti's theorem and a bunch of math to get a distribution of the estimand. And in there, we need a model for the propensity score if we don't have an experiment. So I don't see why it's not possible. Maybe the packages aren't developed. I'm not sure, honestly, but it's a very interesting question. I think it's not easy to answer so superficially right now, but I think it's worth looking into. Maybe we can go to a next question. Thanks, Sean. It made me think. I like the question.
So maybe I can take a question from Salkain, I believe.
Yeah,
there's a very interesting question about, and it's actually related to the instrumental variables. And what is mentioned in the question is that most of the packages are related to GWAS studies, so genome-wide association studies, and instrumental variables there. It is true, a lot of packages are related to that field, because there is a whole area of causal inference which we call Mendelian randomization, which generally uses genome data, so genotypes as instrumental variables, exactly as we were explaining in the communication with Alexander, that we can use genetic data which is associated with some modifiable factor, biomarker, and then simulate that as having some treatment, some counterfactual design. And we know for a fact that genetic data is not associated by confounders. The genetic data is something that we get at birth, and there are mutations that make some changes, but generally the genotypes can be considered relatively static. So we know for a fact that they can be used as instrumental variable in many situations to identify the causal inference of biomarkers or other modifiable risk factors with the disease. As Justin said, it's highly probable that since this is one already highly developed field, a lot of packages are revolving around that field. But I think there are a lot of packages that are in development now and will be developed in the future, which may be associated with other fields. Justin mentioned that instrumental variable regression is highly used in social science, econometric models, but it's used more and more in life science, because there are situations where we can use them. But on the other hand, a lot of data is created out there, and it's not easy to find an instrumental variable. And usually the go-to is to go either to inverse probability weighting, or just using some other way of calculating the propensity score, doing the matching, and so on. Any question that you would like to take, Justin?
I would love to, but I think we're running out of time. I think we should end. There's a few questions left. So I see James has a question and others. I'll take time, and maybe Darko too, to answer in the questions in the comments on LinkedIn with our keyboard. So we can end at 11 like we planned. So I just wanted to thank everybody. This was really amazing. I'm happy that we had questions, and thanks for the kind words for people that encourage us. Alex, it's really great that you were here, and if you're interested, check out the group that I'm doing. Alex is working with me on the group, so I think he's a great leader for the group. He's done so much for Causal Inference. You can also check out his podcast. And thanks, Darko, finally taking the time to get together with me. We've been talking on LinkedIn for a while now, and it's great to actually do something together, and I hope we can do more in the future.
Thank you so much, Justin. It was really a pleasure to do a podcast with you. Hope we can do more in the future. I would like to thank everyone who attended and everyone who left comments, suggestions. Thank you so much, and looking forward to seeing you in some discussions in the future. And hope that you enjoyed the podcast. And again, big thanks to everyone who supported us, and see you soon.
All right. Thanks, Darko. Bye, everybody.
Bye, everybody.
Thanks.